Hey, what's up? It's your old pal, Mr. Cook. We're working on the probability review. We just got done with the first page, so let's move on to the second page. And it looks like these ones are all just going to be simple probabilities. According to a local college, the probability that an incoming freshman will graduate in 5 years is 31%. What is the probability that they will not graduate in 5 years? So both of those probabilities are what we call complements of each other. So it's like that they graduate would be 31%, and so that they don't graduate would be everything else. So the way that we find everything else is take that 31% away from 100%. So 100 minus 31, that's 69, so it would be 69%. So there's a 69% likelihood that they will not graduate in 5 years. A fair coin is flipped, and a spinner with the numbers 1 through 5 is spun. What's the sample space? Well, for flipping a coin, that'd be heads and tails. And then the spinner is numbered 1 through 5, so you get a heads and a 1, a heads and a 2, a heads and a 3, heads and a 4, heads and a 5. Or you could get a tails and a 1, a tails and a 2, tails and a 3, tails and a 4, tails and a 5. That'd be the sample space. You just have to list off all of the different options that you could have for the pairing. Find the probability of getting a heads and also spinning an odd number. So I'm guessing that that's like back to back. So the probability of getting a heads, you're either going to get heads or tails, so that'd be a 1 and 2 chance. And then you multiply that times the probability of spinning an odd number. So the odd numbers out of 1 through 5, so if I have 1, 2, 3, 4, and 5, I have 1, 3, and 5 that are odds, so that's 3 out of the total of 5 numbers. So if I just multiply these fractions together, 1 times 3 is 3, 2 times 5 is 10, so it's 3 out of 10 for our answer. What's the probability of getting a heads and then not spinning a 3? So probability of getting a heads is going to be the same, 1 and 2, or 1/2, and then not spinning a 3. So the only thing that I don't have to get is the 3, so that'd be 4 numbers out of 5. So I multiply those together. 1 times 4 is 4, 2 times 5 is 10, and that'd be my answer, but I can reduce that because 4 and 10 are both divisible by 2, so I'd have 2 over 5, and that would be my answer overall for number 6C. For number 7, 2 urns both contain red balls and white balls. Urn 1 contains 5 red and 7 white. Urn 2 contains 9 red and 3 white. A ball is drawn from each of the urns. Are these events independent or dependent? Well, independent events means that the probability of one doesn't affect the other, and dependent means that the probability of one does affect the other. So, like usually what this means is if they're dependent, that means that the actions of doing one of them somehow alters the sample space of the other. So if I've got these 2 urns, urn number 1 and urn number 2, you can see that like if I get one of the red or the white balls out of urn 1 and keep it or put it back in, it doesn't affect any of the probabilities for urn 2, like getting a red or a white ball out of there. So in this case, these events are going to be independent. What's the probability that both balls drawn are white? So if we reach out into urn 1 first, there are 7 white balls out of a total of 12 of them. So that'd be 7 out of 12. Then we multiply that times the other probability of getting a white ball. So there are 9 plus 3, so 12 balls in that one. And there are 3 white ones. So we multiply these values together. 7 times 3 is 21. 12 times 12 is 144. And then you can reduce this a little further because both of these are divisible by 3. So 21 divided by 3 is 7. And then 144 divided by 3, that's 36. So 7 out of 36 would be your probability. What's the probability of drawing a red ball from urn 1 and then a white ball from urn 2? So if we go to urn 1, we'd get a probability of let's see, 5 red balls out of 12 total. And we multiply that times a white ball for urn 2. So that'd be 3 white balls out of a total of 12. So once again, we can reduce this a little further, like when we multiply it out, so that's 15 out of 144. And these are both divisible by 3, so it'd be 5 out of 36 for the probability overall. All right, next up, you draw a card from a standard deck of cards. You're now going to draw a second card. All right, so describe what would make this an independent event. So remember that it's independent if it changes the sample space. So like if I draw the card out of the deck, and let me see, I got a deck of cards over here. There they are. So like if I take this deck of cards, right? The sample space is the same as it is on that sheet that you guys have that shows all of the, different cards that you have, like the different sample space, the different suits and all that kind of stuff, right? So if I took a card out of here, and it's a 2, right? If I put the card back, then it doesn't change the sample space. That card's still there, right? So the probability of getting a 2, if I shuffle the deck up a little bit, is still the same, like there are 4 2s in there, so it's still 4 out of 52 total cards. But if I took that card and I took it out, like if this was still a 2 and I took it out, there'd be 1 less card in here, 1 less 2 in here, so the probability of getting another 2 would be less likely. So that's an example of what makes things dependent versus independent. If I were to replace the card back in there, it puts everything back to normal with the deck of cards, and so that means that the probabilities wouldn't change. So what would make this an independent event would be if I were to pick the card first, pick the first card, and not replace it in the deck before getting that second card. To make this a dependent event, I'm sorry, wait, I got those backwards, didn't I? Independent would mean that it would not change the deck. So if I replace the card, so if I pick the first card and then replace it back in there, that would be an independent event because it wouldn't change the likelihood of the second event, okay? A dependent event, it causes the next event, which is drawing the second card, to change its probabilities. So in this case, a dependent event is if I were to pick out the first card, and that's the one where I would not replace it. Man, so I got those mixed up when I was answering the questions, but it sounds like I got it the first time around. Let me just reiterate just in case, because I got a couple seconds before I can turn this video off. Just a reminder, independent means that it doesn't affect anything. So for an independent event, if I were to take the card out, okay, whatever it is, in this case it's an ace. If I put the card back in there, there's now 52 cards, there's 4 aces, nothing has changed. But if I took the card out and I didn't replace it back in, there's less cards to deal with. There's 1 less 10 in there, and so it changes up all the probabilities. So that's what would make it dependent. Okay, so independent, it keeps the probabilities the same. Dependent changes the probabilities up from event to event. Okay, so that's the end of the second page. Most of this stuff can be found again in the probabilities on, I think, like 8.3 or 8.4. So just check those out. And that's the end of this video. And then on to the next one, so on to the next page.